did together problems number 1 through 3 the other day with our system schema. That's what this thing is called. And our force diagrams. So I'm just going to go through and do the rest of these. I'm not sure how long this is going to take us, honestly. We might get done pretty quick today. All right, so for problem number 4, we've got a chandelier suspended from a ceiling by a chain. And so first what we need to do, if we're going to draw it for our chandelier, we need to keep in mind that there's only 2 things that our chandelier is interacting with. One is the chain, and the other one is the earth, right? Because we're on earth, so we're always going to have that. I'm going to write chandelier, even though maybe I could have just gone with light, and that would have taken me less time. So there's our chandelier. And then it's using the chain to hold on to the ceiling. So you could say chain there, you could say ceiling, and that would be okay because you're going to end up with the same forces. It's also interacting with the earth. And so there's our system schema. For our force diagram, we're going to reduce the chandelier to a dot. We're going to have a force of gravity on the chandelier. I'm going to just abbreviate this and shand. By earth. And then upward, we're going to have a force of, I'm going to say tension. Tension's really your best choice with this problem. And again, that's on our chandelier, by the chain, or you might have by the ceiling, and that's okay. And our chandelier isn't moving. It's not accelerating anywhere. The accelerating is the important part, but these are balanced forces. So those are going to be equal and need congruent marks to show that they're equal. You guys have any questions about number 4? Okay. Number 5 is a similar problem. We've got a thing that's hanging on a chain or a rope. And so again, here we've got our bucket in the middle. That's the thing that we're interested in. And it's on a rope. The rope is going over the loop, but we're worried about the bucket. We don't care so much about the forces on the rope. And then this thing is being pulled downward by the earth. So if we reduce our bucket to a dot, there's our bucket. We have gravity on the bucket, our victim, by the earth, because we are on the earth. And then our upward force is going to be, again, tension on the rope, on the bucket. Remember, our force diagram has to have only the victim for all of our forces has to be the same by the rope. And those are equal. So I'm going to have congruent marks. Anybody have questions about number 5? Okay. Number 6, our skydiver has left the plane and is still speeding up. So he is accelerating. It says label the forces and use equality marks on the force vectors. So we've got a skydiver. And our skydiver is probably going to have an interaction with the earth, right? Because he's heading towards the earth. And he might be having a little bit of an interaction with the air. He hasn't let his shoot out yet, so it's not really a lot, but there may be some interaction there, but not enough really to slow him down. If you've ever seen something falling from the sky, you know that it's not. You have to have a lot of surface area to be able to slow it down, to be something like a plane or a parachute and move more slowly. So we're expecting that this is the overwhelming force because he's still speeding up. And so when we see this still speeding up or we see something accelerating, that's telling us that our forces aren't balanced. That's what that's a clue about. Not balanced forces. If it's not balanced, then we're not going to use congruent marks because one's going to be larger than the other one. So if I'm focused on my skydiver for my force diagram, I'm going to draw a dot representing my skydiver. Then I'm going to have a force of gravity on skydiver by earth. And then upward, I've got maybe some drag. Skydiver But these two are not equal to each other. This one's going to be much bigger because we're speeding up as we're falling. All right. Do you guys have any questions about number 6? This one's a little bit trickier because I'm kind of asking you guys to accept this just because I'm telling you that. Again, that's something I want to kind of play around with in the next couple days. Okay. Next, this skydiver has a parachute. He's like in a Bond movie or something. I don't know. He's diving in a suit, and I imagine that's a Bond movie thing. But he's got a parachute, and that's letting him fall at a constant velocity. So this is no acceleration. When we have no acceleration, it's telling us that our forces are balanced. All right, so this guy, we've got our skydiver. He's falling to the earth, and he's got a parachute. Yay! He probably feels very relieved that it works. So here's our skydiver falling to the earth. We've got drag from our parachute, and those things are equal because there's no acceleration. So we've got drag on skydiver. By Earth. All right. Now we've got another pair. We have a ball that's been thrown. Here we're looking at something that's got that's rising in parabolic trajectory. Down here we have one that's at the very top. And what you'll notice from both of these things is that they are not touching anything. If they're not touching anything, then the only interaction that the ball has is with Earth. And that's going to be true for both of these. So we've got a ball, and the ball is interacting with Earth. And you can even imagine that these are two different points in motion for the same object. Here it is as it's rising. This is it at the very top before it comes down on the other side. So if the only interaction is with Earth, then there can only be one force that this is experiencing. And if there's only one force, and our force diagram is only going to have one arrow, right? There's only one connection here. That connection has to be gravity. So I'm going to reduce my ball to a dot, which conveniently kind of looks like a ball. And then I just have the downward force of gravity on the ball by Earth. I'm going to have the same thing down here, guys, because the ball isn't interacting with anything else that's going to impart a force on that ball. So here we've got gravity on ball by Earth. So those two are the same. The forces that are acting on that ball don't change throughout its path. Does anyone have any questions about that one? Okay. Guys, we're going so fast today. Okay. Draw a force diagram for a cork that's floating in water. So if we have something that's floating, it's not moving in either the upwards or downward direction, and it's certainly not accelerating in either of those directions. If it's just floating, it's kind of just passively existing there. And so we've got the cork. The cork is interacting with Earth, and it's also interacting with water, right? I'm drawing the water on my system schema because it's below it, but the water is actually pushing up on the cork and the Earth is pulling down. And so those are going in opposite directions. So when I draw it as a force diagram, just as everything else, I've got the force of gravity on my cork by the Earth. And then I've got an upward force that's buoyant force. Let's see if I can spell it correctly. B-U-O-Y-A-N-T. So I've got buoyant force on the cork by the water. And we're told it's just sitting there. It's got no velocity. It also has no acceleration. No acceleration tells us that these are balanced, and I need to draw congruent marks. All right, airplane. We talk a lot about airplanes at my house as my husband's been taking some pilot courses. So there are a lot of YouTube videos about flying if you want to understand things about flying. I had no idea, honestly. Um, so this is a force diagram for an airplane that's in straight and level flight. And so I'm going to, let's see, plane. Our plane is interacting with the Earth, right? It's still going to experience gravity. If you've ever flown in a plane, though, you know that it's not sitting on the Earth or heading towards it. Ideally, if you're flying your airplane, it's flying in a in a straight and level way. And the reason that it can do that is because it's also interacting with the air, the atmosphere around it. Um, it does that by using a special shape on the wings to produce lift. And so it's basically using the density of the air to be able to generate an upward force so that it can stay up in the air. Birds have been doing this for much longer than humans have. And you know, this is really great physics. It works. Planes want to stay in the air. So I'm going to reduce my plane to a dot. I'm going to draw my force due to gravity on the plane. Yeah, P's not very good. By Earth, but it's not falling, it's not accelerating towards the ground. So I've got an equal and opposite force that's upward that is called lift by air. All right, we'll talk lots about planes in physics class. There are lots of really great examples for them. But this is what we're concerned about here. If we're in straight and level flight, you could kind of go the advanced thing here. There's multiple ways that the plane is doing things where it's interacting with the air. There's actually two more that you may have picked up on. One is that there's going to be a little bit of drag. And there's also going to be forward thrust. So thrust on plane. And those two are also equal and opposite as long as our airplane is not accelerating. So this is how you would do a second set of congruent marks. You just do two instead of one. So if you did one for each of those to indicate that they were the same as each other, you would also be accidentally inferring that it was the same as these two vertical forces, which isn't really the case. And that's not telling you about the directions, it's telling you about the magnitude of those forces. That's what those congruent marks are meant to represent. So you may have just gotten the up and down one, but if you also included the side ones for this one, that's okay too. Anybody have questions about the airplane today? I can't see you guys, so if you do, yell at me. Did somebody, by the way, hold on. So make sure you guys didn't leave a comment. Okay. Because I heard that little ping noise, and sometimes that's a comment that happened in the chat. Okay, last one. This is a nail that's been picked up by a magnet. So we're going to try to label the forces here. This magnet is holding onto this nail so that it's not falling. It's also not going up through the magnet. So there's kind of a lot of things going on here. There's kind of a hidden one that you guys might not have noticed too. So we've got our nail, right? That's what we're interested in. Force diagram for a nail. It's interacting with the earth, and it's interacting with a magnet. Okay, so there's one tricky part for this one. I'm going to show you guys what it is. So our nail is experiencing gravity. Gravity on nail by Earth. It's got an upward force from the magnet, so that's magnetic force. We also have a nail that's not going through the magnet. So what we don't actually know is if this has more magnetic upward force than gravity pulling it down. But the reason that our nail doesn't go through the magnet is because it's also experiencing a normal force from the magnet. So remember we talked about normal forces, it was always perpendicular to a surface. So if we're looking at just the corner here, it's going to be a straight down normal force there. And so when we're considering our force diagram, we really should include that as another force that is downward. And so what a lot of folks do, we're going to attach the tail here, and it's probably not as big as gravity. So I'm just going to write a littler force in here. So our normal force on the nail by a magnet. And it's actually pushing the nail away from the magnet and keeping it from going up into the magnet. So when we're thinking about this in terms of how big are these forces, we've drawn these congruent lines before. This is the first time we've seen two going in the same direction. And so what this is actually telling us is that our upward force, our magnetic force, is equal to, hold on, our normal force plus gravity, and it's actually the negative of that, right? So these would be negative, the value for that. So if we were trying to set these up to solve a problem, we would have to recognize that these two combined have the same magnitude as our magnetic force. And so that's something that we're going to see more of as we go on through this unit. Okay, so that gets us through all the problems on that worksheet. Do you guys have any questions about any of that stuff? I can't see you right now, but I'm looking at the chat. We can also talk about them in classes. We'll continue to work on problems like this.